Okay, let's unpack this. Welcome. We're doing another deep dive today using some really interesting source material you shared. So today's topic is maybe a bit unexpected. It's about calculus.
Yeah, specifically integration.
Right, integration,
Yeah,
but applied to forestry.
exactly. The sources we have are discussions around calculus in forestry.
Hmm.
They focus on how people figure out the economic value of forests over, well, a really long time. They call it forest economic value.
Okay, so our mission here is to really pull apart these sources. We want to see how integration is actually used, and understand why it's the tool they reach for.
hmm
And crucially, connect it back to you, the listener, especially if you're maybe wrestling with calculus homework right now. See why it matters.
It's pretty fascinating, actually. These sources draw a very direct line. They basically say calculating the total economic value of a forest rotation.
Okay, what's the exactly like the whole life cycle?
Pretty much. From planting the trees all the way to harvest, which could be, you know, 80 years later, maybe
Hmm.
more. Calculating that total value, according to these forest resources technology discussions, it relies fundamentally on integration.
Huh. So it's not just some theoretical math problem, it's about putting a real dollar value on a forest as it grows
Yeah.
over decades. But why integration? Why not like simpler math? Can't you just figure out the final value and multiply or something?
Well, that's the thing the sources really get into. A forest's value, it doesn't just increase steadily. It's not static, not linear.
Yeah.
Think about it. The rate timber grows, changes, right? Faster when young, slower when older.
Okay, yeah,
And market prices for wood, they go up and down.
true.
Plus, you might have other values like carbon credits or recreation fees. Those could add up at totally different rates, maybe fluctuating rates too. Integration is the mathematical tool built for summing up quantities that are changing continuously, or where the rate of change itself is variable over time.
Ah, okay. So the sources are telling us it's not about just taking a snapshot value. We're adding up value that's accumulating constantly, year by year, maybe even faster than that, based on all these shifting factors.
Precisely.
And the integral is what lets us capture that whole accumulation process accurately.
Exactly right. And it's not just about the trees getting bigger, the physical growth. It's the economic value. The sources off frame it as integrating a function that represents the net revenue rate, or you could call it the rate of value increase over time.
Net revenue rate.
Yeah, and there's another key piece the sources mention, discounting.
Discounting, you mean like money in the future isn't worth as much as money today?
That's the one.
How does that fit into the integral? It seems like another layer of complexity.
It is, but it's crucial for realism. The sources point out, if you want the present value of a harvest that won't happen for, say, 50 years, you have to discount that future money back to what's worth today. So when you integrate, you're summing up that rate of value building up over time, but that rate itself is constantly being adjusted downwards by a discount factor.
Whoa.
And that discount factor also changes continuously the further out you look into the future.
Okay, got it. So the function inside the integral gets pretty involved then.
It can, yeah. But the sources stress that this is essential if you want a realistic economic picture.
That's a really important detail from these readings. Integration isn't just adding up a simple rate. It's adding up a time-discounted rate of value growth over that whole long rotation. That feels much more, well, sophisticated. And it directly uses what you learn about functions changing over an interval in calc class.
It really does. It just highlights how calculus gives us the tools to model and analyze systems where change over time is absolutely fundamental. It lets forest managers, economists make these big long-term decisions based on a value that's cumulative and adjusted for time.
So pulling it all together from this material, the next time you're grinding through an integration problem, maybe picture a forest. This math, it's not just abstract stuff. It's really used to understand the complex, decades-long financial life of a forest.
By integrating these changing rates of value, adjusted for the time value of money, it's a powerful reminder, I think, that these calculus rules, they have a very real, very tangible applications. They help quantify value that only really unfolds over long stretches of time. Which kind of leads to a final thought for you, the listener, maybe something to chew on. If calculus, specifically integration, is so vital for figuring out the total economic value of something complex like a forest over decades, where else?
Yeah.
Where else in the world around you might things be changing, accumulating value or effects over time in ways that perhaps only integration could truly capture? Think about that.